An event is something that occurs at a particular time and particular place. For instance, you pressing play to watch this video is an event. But time and space are relative, so observers in different frames don't have to agree on the time and space locations of an event. For instance, say we have a frame S in which I measure the coordinates of an event to be x, y, and t. Then in a frame S prime that is moving with velocity v along the positive horizontal direction relative to S, I would measure different coordinates x prime, y prime, and t prime that are given by the Lorentz transformation. The time coordinate transforms as t prime equals gamma t minus vx over c squared, where gamma is the relativistic gamma factor, 1 over root 1 minus v squared over c squared. The space coordinate that is parallel to the relative velocity between the frames, so here the x coordinate, will transform as x prime equals gamma x minus vt, while an observer in the frame S prime will measure the same space position y in both frames, y prime equals y, because here the y coordinate is perpendicular to the relative velocity between the frames. Now, the fact that different observers can measure different times for the same event might seem kind of weird, and that's because we're not used to seeing this in our everyday experience. In particular, for velocities much smaller than the speed of light, so for v much less than c, gamma is about 1, and so this v over c squared term is really small, and so for very small velocities, t prime is about t, and we wouldn't see it transform at all between different frames. So let's explore this issue that time is relative in a problem. In a frame of reference S, two events happened. At spacetime coordinate x1, t1, Julius Caesar was alive, and at a later coordinate x2, t2, he was dead, betrayed by Brutus. But we like Caesar. Is there some way we can use the laws of relativity to save his life by warning him about Brutus's intentions? Does there exist a frame of reference S prime moving with speed v with respect to the frame S in which the sequence of events appears reversed? We're told to consider spacetime events x1, t1 and x2, t2 in the frame S, where this first event, which we'll call event 1, occurs at a time when Caesar is still alive, and event 2 corresponds to a time when he's dead. So we're not given specific values of the coordinates x1, t1, x2, t2, but of course in this frame S, t1 is less than t2 because he's alive before he's dead. And we'll also take x1 less than x2. So this isn't a necessary assumption to solve the problem. It turns out it'll just make the algebra a little bit easier later on. This is just like choosing a convention that the event 2 happened to the right of event 1, which isn't going to affect the outcome of the problem. Okay, so using the appropriate form of the Lorentz transformation here, we can write these coordinates x1 prime, t1 prime in the frame S prime as gamma x1 minus v t1, and then t1 prime is gamma t1 minus v x1 over c squared. And the event 2 in the primed frame is going to be given by exactly the same thing, but with 1 goes to 2. So x2 minus v t2, gamma t2 minus v x2 over c squared. Good. So the question is, can we find a velocity v that the frame S prime is moving relative to S, such that t2 prime is less than t1 prime? That's the question. So the first step, we'll just plug in for t2 prime here and t1 prime here, and we can go through the algebra to simplify this equation in terms of these relations. So check yourself against the solutions to see that you do that right. And in the end, we'll find that this equation that we're trying to see if it's true simplifies to c t2 minus t1 over x2 minus x1 less than v over c. So this is an equation that says a velocity such that t2 prime is less than t1 prime would have to satisfy this inequality. Okay, good. So before we go any further, I'm just going to define a quick notation. So I'm going to call delta t, t2 minus t1, and delta x, x2 minus x1. So delta means 2 minus 1, and that's just going to simplify some of the equations that we write. So I don't have to keep writing t2 minus t1. All right, so here's the first crucial point. The velocity v has to be less than or equal to the speed of light. Therefore, v over c is less than or equal to 1. Now, there's no hope of this inequality possibly being satisfied unless this left-hand side is then less than 1. Since v over c is less than or equal to 1, therefore the separation between the events has to be less than 1. This is an important point, so let's say it again. As long as the relative velocity between the frames is less than or equal to the speed of light, then the only possible way for me to be able to see the events reversed in the frame S prime is for delta x to be greater than c delta t. If this is the case, then I will be able to find a velocity v that is greater than c squared delta t over delta x. So the question boils down to, is this the case? Can the space-time separation between the events be such that this is true? So let's ask ourselves, what is the maximum spatial distance between the two events? Well, an observer at event 2 knows about event 1. They know about Caesar's life. That's the setup of the problem. I want to go help Caesar. And the fastest that information could have possibly traveled between events 1 and 2 is the speed of light. So what's the distance that light travels in that time? Well, it's the speed of light times the time separation. That's the distance that light would travel in the time between events 1 and 2. And that's the maximum possible spatial distance is c delta t. So if this is the case, then in fact what I have is delta x being less than or equal to c delta t. So x2 minus x1 can't be bigger than c times t2 minus t1. And this is because the information had to get to me in order for me to know I needed to go back and save Caesar. So unfortunately for Caesar, we have our answer. No, this is not the case. No, I cannot find a frame of reference that is moving with a velocity less than or equal to the speed of light, such that I see the events reversed, such that I see him dead before I see him alive, so I know I can go back and warn him. So unfortunately for him, I just can't move fast enough to go and warn him about his impending death.